Before we go into the example problems for section 6.3, I want to reiterate and summarize inductors and capacitors in series and parallel. Now, the key idea that we want to remember is inductors in series behave pretty similar to resistors in series. So inductances add in series. Now, inductances in parallel behave pretty similar to resistances in parallel. Okay, so the sum of reciprocals of the individual inductors is equal to the reciprocal of the equivalent inductor. Okay, similarly for capacitors, capacitors in series behave like resistances in parallel. It's not exactly behaving, but they transform their equivalent relationship is similar to that in resistances. So behave is not the exact word. Capacitances in parallel add like resistances in series. Okay, so let's look at an example problem, a simple example problem where I have a ladder of inductors and we are trying to simplify the equivalent resistance between the terminals A and B. Where do I begin? Well, straightforward. Look at these two inductances. They are in parallel. Okay, when they are in parallel, the inductance equivalent of this guy is L1 times L2 by L1 plus L2. Okay, you can do the exact same thing by 1 over L equivalent. You will arrive at the same result is equals to 1 over L1 plus 1 over L2 because they're in parallel, and in parallel the sum of their reciprocals is equal to the reciprocal of the equivalent. Okay, so what is 20 in parallel with 30? Okay, you can do that and you will find out that this equivalent resistance or equivalent inductance is equals to 12 Henry. Okay, 20 into 30 by 20 plus 30. Okay, the rest of the circuit comes along for the ride, as Aguilar likes to call it. Okay, the rest of the circuit comes along for the ride. Okay, now there you go. Perfect. Now we can further simplify this by noting that these two inductances, the 12 Henry inductance and the 8 Henry inductance, are in series. So in series, they simply add. So what I'm going to do is to keep the rest of the circuit as is. Okay, I want to keep the rest of the circuit as is and replace these two. Okay, the ones that I'm going to replace are these two with their equivalent sum. Okay, because this is series of inductances. I have what? 8 plus 12. The sum is 20 Henry. Okay, so we are decomposing this circuit step by step. Now what can we do? What we can do is to notice that these two inductances are in parallel, 20 in parallel with 20. Don't do the math where you don't have to. Okay, 20 in parallel with 20 is 20 times 20 by 2 times 20 plus 20, which is 40. Okay, so 10. When you have two resistances in series, it does not matter. One is 100K and the other is 100K. The equivalent resistance is always going to be 1/2. Okay, 1/2 kilo ohms, 1/2 of that. And then we see that the solution here also is exactly 1/2, right? The equivalent of those. So again, we do the rest of the circuit, we bring it in as is, okay? And then the resistances that are in parallel, I'm going to replace them with one resistance that is the equivalent, which is the half of those two, 10. Okay, so resistances, inductances add in series, and then in parallel, they reciprocal. Sum of the reciprocal is equals to the um, reciprocal of the equivalent. So here we have another series combination. So I'm going to replace that. So you see, step by step, this is a pretty simple, straightforward problem. Okay, so that part I'm going to replace with its equivalent inductance. Okay, because they're in series, they're going to add 10 Henry plus 10 Henry is going to be 20 Henry. Now, 20 in parallel with 20, right? Let us see. That's the next part of my equivalent circuit. Okay, all I have to do is to notice that these two 10 and 20 are in parallel, and because they're in parallel and they're equal, what happens is these two become half. The equivalent becomes half. Let me see if I can duplicate that, and I'm going to get rid of this, and then this guy is 20 in parallel with 20, which is 10 Henry. Okay, again, decompose the same thing. 10 in series with 10, you should have it 20. Okay, so I have 8 Henry over here, and then there is a 30 Henry over there. There is my A, there is my B, and this guy, which is the series combination of 10 and 10, is 20 Henry. Okay, dang it. Now, let's go back and see if we can notice that this guy and this guy are in parallel. 20 in parallel with 30. We did that math already. 20 into 30 by 20 plus 30. Okay, 20, 30, 20 plus 30 is 12 Henry. So I'm going to replace that orange block like so. This is 8 Henry. And then this orange block, I'm going to replace it with 12. You see, it's a pretty straightforward problem. Okay, now this comes out to be 20 Henry. That is the total equivalent between A and B. Okay, that's exactly what we wanted to find out. Given this circuit, the problem is find the L equivalent between terminals A and B. And what we started doing is that by looking at these two in parallel, we replaced it with one inductance. Then these two inductance are in series. We replaced it with one inductance. Then we have a couple in parallel. So hierarchically applying the series and parallel combination of inductances to make sure that the final simplified circuit between A and B, okay, between A and B is a simple value, as simple as we can bring it down to be. We have it to be 20 Henry here.